Section 3.2, the chain rule. Now, before we jump right into the calculus, the derivative using the chain rule, we first need to recall what is a composite function. And so recall that a composite function is really this idea where you have one function taking another function into itself entirely. And so we're going to say that one of the functions is the inside function and one of them is the outside function. And so we're going to say that the one inside the parentheses is inside, and then the one on the very outside, so f here, is the outside function. And so we're going to have to realize there's an inside, there's an outside. Alright, so first let's remember how to compose functions. So if I want to find f of g of x, and I also want to find g of f of x when I'm given these two functions. So let's find first f of g of x. Okay, so what do? All we're going to do is we take the entire g function and you plug it in to the f function. That's all. And so everywhere you see an x, put a parentheses and replace it with g. So f of g of x is then going to be 2 times x squared minus 7x plus the square root of x squared minus 7x. And so in this situation, g, or x squared minus 7x, is our inner function, and f, that is 2x plus square root of x, is our outside function. Okay, that's our composition. And then of course we could go through the steps and we could simplify this completely, but since we're just composing, I'm going to leave it there. Then let's go the other direction. Let's find g of f of x. G of f of x, this time we take the entire f function and we're going to plug it into the g function. And so that everywhere we see x, we're going to put parentheses around it and replace it with the f function. So g of f of x is then going to be, in parentheses, 2x plus square root of x, quantity squared, minus 7 times 2x plus root 7. And once again, of course, we could simplify this, but since we're just trying to make sure we can do compositions, I'm not going to worry with the simplification here. Now, what's really going to be far more important for us is that we can identify compositions. And so what we're going to want to be able to do is find two functions, given an initial function, where you could tear it apart as some inner and some outer. Now, usually, this is as easy as writing a box around the inner function to recognize that that's your inner function. So for this number 1, I see that this set of parentheses actually lends itself to trapping that inner function. And so if the inner function is x squared minus 3 times x, that means that my inner function here, g of x, is really just x squared minus 3 times x. Well, if that's the inner function, then notice that the outer function is then going to be the parentheses, but what's going to be there instead is an x all to the 4th power. And notice that if you did exactly what we were doing earlier of finding composition, then you could put g into the f function, and then notice that you would get exactly what we have here as the composition. And that's what we needed to see. We needed to see how to break it apart as a composition of functions. Now, let me make a statement real quick, and that in general, when we're finding compositions, it is always true that you could do the trivial thing. Trivial is just easy or obvious. And the trivial thing is let x be your inner function. But in terms of our derivatives, that's never really going to be helpful, and so that's not the way we want to approach this. Alright, so for number 2, I'm looking for an inner function, and then I'm looking for an outer function. So let's look for an inner function, let's block it off. Well, this is a little weird because you might have to block off multiple things. That's okay. Well, I see that I've got a square root of x, and I see that I've got a square root of x. Then, that tells me that my inner function could be the square root of x. And my outer function could be, just replace all of our boxes with x's now, that's going to be x divided by x plus 3. And so that's how I could find a composition, an inner function, and outer function. Alright, so now that we've figured out identifying some compositions, let's actually get our chain rule. So, if we have a composition of functions, that composition of functions is going to be f of g of x. and I want to take the derivative of my composition. Then that's actually going to be the derivative of the outer function, leave the inner function inside unchanged, times the derivative of the inner function. Alright, the derivative of the outer function, leave the inner function unchanged, and then times the derivative of the inner function. That is our chain rule. Now let me make a side note real quick. The truth is that this chain rule can be iterative. What do I mean by that? I mean that if you have a composition of a composition of a composition of a composition, however many layers deep, you could just keep taking this rule and applying it further and further down to the chain, okay? That's why it's really called a chain rule, is because that chain can build as big as you need it to. Alright, so let's try this. So, we're given two functions, f of x, g of x. Well, they're going to ask two things. First, they want us to find f of g of x. So let's do that first. That's the straightforward part. F of g of x. Composite function. Inner is g, so we take g when we plug it into f. Alright, that's then going to be 1 divided by 1 minus x squared. Okay, that's fine. Now we want to find the derivative of that composition. So, let's take the derivative of f of g of x. Now, you could write this one of two ways. You could write it like this, knowing the two separate pieces. Or you could have written it as the derivative of 1 divided by 1 minus x squared. Either one is perfectly fine. Okay? Now, for the time being, this f of g of x, using the chain rule, it might be easier to find a couple things. Find f prime, find g prime, and then just plug everything back in like it's supposed to. So since we know what f is and we know what g is, let's do exactly that. Let's find f prime. Alright, what is f prime of x? Well, remember that f of x, being 1 over x, is really the same thing as x to the negative first power, right? And so then the derivative, f prime of x, is the same thing as negative 1 times x to the negative second. So that's just negative x to the negative second, or negative 1 over x to the positive second. Either of those is perfectly fine. So we found f prime of x. Then let's find g prime of x. G prime of x is then going to be, well, this one's not so bad. 1 minus x squared, the derivative of 1 is 0, and the derivative of negative x squared is going to be negative 2 x to the first power, and so now we found g prime of x. Then let's do one more small step. Let's find f prime of g of x, since that's this first part of my chain rule. But f prime of g of x is just going to be negative 1 divided by, plug g of x into f prime, and that's going to be 1 minus x squared, quantity squared. So there's f prime of g of x. And then we've got g prime of x. So this is then going to be negative 1 divided by 1 minus x squared, quantity squared, times g prime of x, which was negative 2x, which then we can simplify a little bit. That's going to become negative 2x times negative 1, or positive 2x, divided by 1 minus x squared, quantity squared. And I'm going to say that that is the derivative of this composition. Now, a few notes here. Notice that we were really trying to take the derivative of this function. Did you have to use the chain rule? The answer is no. You could have used the quotient rule. But the chain rule becomes more useful. And just to give you a heads up as what's going to happen in the future, and what I'm going to end up doing, is I'm really going to end up rewriting these in such a way that I see the composition happening. And so I'll see that this is really the same thing as 1 minus x squared to the negative first. Then I'll take the derivative of this thing, noticing that my inner function is 1 minus x squared, and my outer function is really this thing raised to the negative first power. And so just pointing out that there's different ways to view this chain rule. Alright, let's try it again. this function can be viewed as a composite function. And this is actually what I was trying to tell you just a moment ago by pointing out there's different ways to view this. But let's see what we could do. Alright, so if I'm given an h of x and I want to think of it as a composition f of g of x. F is my outer, g is my inner. Then it's perfectly fine for you to state, oh, well then I can see that f of x is really the entire function raised to the 7th power, so x to the 7th. Then my inner function, g of x, would of course be this polynomial inside the parentheses, which is 9x squared plus 2x minus 5. Great. Inner function, outer function. Then, via the chain rule, that tells me that h prime of x is really going to be the same thing as f prime of g of x times g prime of x. So if I find f prime and g prime, we can plug it into the formula. So, what's f prime? F prime is just going to be 7x to the 6th power. And g prime is 9 times 2, or 18x to the 1st, plus 2 minus 0. Alright? Then via the chain rule, using our official formula approach, that's then going to be 7 times g of x, which is 9x squared plus 2x minus 5, raised to the 6th power. So that was f prime of g of x, right? All I did was take g of x, plug it into f prime, and that's what I got. But then times g prime, which is 18x plus 2. That's my derivative. There we are. Alright, so we're going to change the game up a little bit. Let's say we have the function h of x that's defined in terms of a differentiable f of x. Now, what do we mean by differentiable? It just means that we are allowed to take the derivative, or we can take the derivative of f of x. There does exist functions that you can't take the derivative of. Those are a problem sometimes. So, let's say that h of x is equal to 17 times f of 2x plus 1. Now, to change our notation to make it match up, let's just call 2x plus 1 our g of x. Then we could think of h of x as 17 times f of g of x. Now, the 17 I didn't do anything with, but let's remember that anytime you take the derivative of a constant times a function, that's the same thing as the constant times the derivative of the function. Therefore, if I want to find h prime of x, it's good enough to say, oh, well that's really going to be 17 times f prime of g of x, now I'm just applying the chain rule here, times g prime of x. And I claim that's exactly how we're going to do this. So, h prime of x is then going to be 17 times, now I don't know what f is, I just know that I'm going to take the derivative of it. So f prime of 2x plus 1, but then we can take the derivative of g, so the derivative of g is just going to be 2, the derivative of x is 1, and so it's just 2. And so then if you wanted to simplify this just a little bit, 17 times 2, that's 34 f prime of 2x plus 1. And I claim that's the best we can do because we don't know what f is. Then for number 4, watch out, it gets a little bit complicated because at this point we actually have a quotient rule with a chain rule inside. Alright, so if you don't see that, first off, we have this square root here, and so we could rewrite this as x cubed minus 7 divided by 6 times x plus 12, quantity raised to the 1/2 power because it's a square root, and square roots and 1/2 powers are the same. At this point, maybe it's easier to rewrite our y. So let's say that I have this y, but let's think of it in terms of functions. Specifically, I see there's a numerator, and I see there's a denominator that's a composition of functions. And so you could really see this as f of x divided by g of h of x. Where specifically in my labeling scheme here, f is the numerator, and that's going to be x cubed minus 7. H is that 6x plus 12 in the denominator. And then we have the outer function of the denominator, which is going to be g of x. G of x is equal to x raised to the 1/2 power. Now, if you were to then take a formula approach, you could do that as y prime is equal to g of h of x times f prime of x minus f of x. Then via the chain rule, that would be g prime of h of x times h prime of x because of the chain rule. But then that's all divided by g of h of x quantity squared. Now, g h of x, that's going to be 6x plus 12 raised to the 1/2 power times the derivative of the numerator, that's f prime of x, that's going to be 3x squared minus the derivative of 7, which is 0, so I'm not going to write that. Now we're to minus f of x, so that's going to be x cubed minus 7 times then g prime of h of x, that's going to be, well, g prime is 1/2 times 6x plus 12 raised to the negative 1/2 power, all times the derivative of h of x. Well, h of x is 6x plus 12, the derivative of 6x is 6, the derivative of 12 is 0, and so that part's done. And that's all divided by 6x plus 12 raised to the 1/2 power, all squared. Then for cleanup, and I'm going to go ahead and add in radical notation here, this is then 3x squared times the square root of 6x plus 12 minus 6 times 1/2 is a 3, and so if I want to distribute that into this binomial x cubed minus 7, I could, or I could leave it out front, but that's going to be 3x cubed minus 21. Make sure you do leave this in parentheses because of course this minus applies to it, and that entire thing is going to be over the square root of 6x plus 12. And remember that a negative power moves it to the denominator of the thing that's being multiplied by, and then the 1/2 power is a square root. Alright, and then that's all divided by, well, this is now 6x plus 12 raised to the 1/2 quantity squared. We're just left with 6x plus 12. For this one, we want to find the slope of the tangent line when x is equal to 9. So we want to find f prime of x if this is our function f. But let's suppose that I want to make this easier. Let's say I don't want to use the quotient rule. Could we use the quotient rule? Of course we can use the quotient rule. But there's a neat little trick that we can do. So let's rewrite this. Well, remember that if you have denominators and you want to move them to the numerator, all you have to do is put a negative power on them, and you've fixed it. So I'm going to rewrite this, and I'm going to rewrite this as 2 times the square root of x plus 3 raised to the negative 1 power. I haven't done anything wrong. I've just used my techniques of algebra to rewrite this. Now we could do this a little better is because, of course, when we're taking our derivative, we need to be able to use the general power rule, and so I need to rewrite square root of x as x raised to the 1/2 power. Now notice that at this point, we actually have a chain rule application. So let's see how this works. Well then, what's f prime of x? Well, the derivative of a constant times a function is the constant times the derivative of the function. Therefore, that's going to be 2 times, now we have our chain rule in application here. This is the inner function, and the outer function is that thing raised to the negative 1 power. So that's then going to be 2 times negative 1 times the inner function unchanged, x to the 1/2 power plus 3 raised to the negative 1 minus 1, which is now negative 2, now times the derivative of the inner function, but the derivative of the inner function is just going to be 1/2 x raised to the negative 1/2, and the derivative of a constant is 0, and so there we are. Now at this point, maybe we didn't really help ourselves, but we can try to clean this all up. This is then going to be negative 2, and then x to the 1/2 plus 3 to the negative second, I can put that in my denominator. That's really going to be x square root of x, plus 3 quantity squared, times, well, 1/2, there's a 2 in the denominator. X to the negative 1/2 moves to the denominator as well, and that's the square root of x. Then cleaning this all up, 2 divided by 2 is 1, that's negative 1 divided by square root of x times square root of x plus 3 quantity squared. But then remember, we're actually going to be plugging in x equals 9 into f prime. So what is f prime of 9? Well, that's going to give us negative 1 divided by the square root of 9 times the square root of 9 plus 3 quantity squared. What's that going to give us? That's negative 1 divided by 3 times 3 plus 3 is 6. 6 squared is 36. 36 times 3 is 108. And so I get negative 1 over 108. Now, we don't have to use the chain rule here. If you would rather, we of course could have used the quotient rule. So let's try that and then double check ourselves. That's going to be the denominator unchanged. So square root of x plus 3 times the derivative of the numerator, but notice that the derivative of the numerator here is 0, minus the numerator unchanged times the derivative of the denominator, which is going to be 1/2 x raised to the negative 1/2 plus 0, all divided by square root of x plus 3 quantity squared. Well, that's going to be negative 2 times 1/2 x raised to the negative 1/2, all divided by square root of x plus 3 squared. But at this point, let's confirm we get the exact same answer. That's going to be negative 2 times 1/2 is really negative 1. Then I have x to the negative 1/2, but that's really going to be 1 over the square root of, now we're plugging in 9, divided by the square root of x plus 3 quantity squared, or the square root of 9 plus 3 quantity squared. That's going to give me negative 1/3 divided by 3 plus 3 quantity squared. That's then negative 1/3 divided by 36. Well, fraction division can become fraction multiplication. That's negative 1/3 times 1 over 36, but notice that's going to give us negative 1 over 108. And the truth is that now you can see that you have multiple choices on the way you approach these problems. Sometimes you may want to use chain rule. Sometimes you may want to use quotient rule. It's up to you. Now let's find the derivative of x squared times 2x plus 3 quantity to the 7th. This is a chain rule inside a product rule. So, step 1, product rule. Product rule says, second function unchanged, that's going to be 2x plus 3 raised to the 7th power unchanged. Then take the derivative of x squared. The derivative of x squared is 2x. Plus the first function unchanged, that's x squared, times the derivative of the second function, which is chain rule, so that's going to be 7 times 2x plus 3 raised to the 6th power times the derivative of the inner function, which is just going to be 2, because the derivative of 2x is 2 times 1, and the derivative of 3 is 0. And so there we have it. I can clean that up a hair. That's 2x times 2x plus 3 raised to the 7th power plus 2 times 7 is 14. 14x squared times 2x plus 3 raised to the 6th power. And I'm looking to see if I see any more simplifications. Not that are super easy, so I'm going to call it right there. More. Now we have product rule with more chain rule. Okay, so f prime of x. Step 1, second function unchanged. That's going to be x cubed minus 10x squared raised to the 7th power times the derivative of the first function. Alright, so we got a chain rule going on. So that's then going to be 4 times inner function unchanged, x squared minus 3x plus 2, and then the rest of our derivative, 4 minus 1 is 3, so third power, times the derivative of the inner function, but the derivative of the inner function is going to be 2x minus 3, the derivative of 2 is of course 0, then plus the first function unchanged, so that's going to be x squared minus 3x plus 2 raised to the 4th times the derivative of the second function. Well, that's going to be chain rule once again. So that's 7 times the inner function unchanged, x cubed minus 10x squared raised to the 7 minus 1, or 6, times the derivative of the inner function, which is then 3x squared minus 10 times 2 times x, and that is it. Let's see if there's a little bit of cleanup. There might not be much. I see that I've got 4 times 2x minus 3, so let's call that 8x minus 12. So that's that piece. I'm going to leave these polynomials to powers alone. That's x cubed minus 10x squared raised to the 7th. I'm not touching it. X squared minus 3x plus 2 quantity cubed. I'm not touching that one. Then let's see if there's any nice cleanup I can do here. I'm going to multiply 7 times this binomial, but that's really all I'm going to do. So plus 7 times 3 is 21x squared. 10 times 2 is 20. 20 times 7 is 140. So that's minus 140x times x squared minus 3x plus 2 quantity to the 4th times x cubed minus 10x squared quantity to the 6th. And I'm going to say that there might be something else we could simplify, but I'm not concerned with it. And so there we are. That's the derivative. Alright, let's find the derivative of this function f of x. So I've got derivative of sums and differences. That's just the derivative of the functions. So let's do what we can, a little bit at a time. F prime of x, the derivative of 2x is just going to be 2. The derivative of 9 divided by x, remember that's really going to be 9 times x to the negative first. So that's the same thing as plus negative 1 times 9 times x to the negative second. Then minus, here I have quotient rule with a chain rule inside. And so that's going to give me the denominator unchanged, x squared minus 7 quantity cubed times the numerator, the derivative of the numerator, which is then going to be 2 times 4, or 8x cubed, minus the top unchanged, that's going to be 2x to the 4th, times the derivative of the denominator, but the derivative of the denominator is a chain rule, so that's going to be 3 times x squared minus 7 raised to the 2nd power times the derivative of the inner function, which is then 2x. The derivative of 7 is 0, and so we have that. Let me be a little bit careful. Where am I? This is all over the denominator squared, which is x squared minus 7 quantity cubed. Now it's that squared. And so let's see if I can clean this up a little bit. That's then going to be 2 minus 9 over x squared minus 8x cubed times x squared minus 7 quantity cubed minus, I see 2 times 3 times 2, that's 12. X to the 4th times x is x to the 5th, all times x squared minus 7 quantity squared, all divided by x squared minus 7 cubed squared. Power to a power rule is multiplication, so that's just going to be x squared minus 7 raised to the 6th power. I'm going to say it's not worth fighting to simplify anymore. And so there we have that one. So let's find the derivative of this one. Notice that this is a chain rule inside of a chain rule. Do we have a chain rule inside of that one? Maybe, let's see. Alright, so how could I rewrite this? Well, I could rewrite this as x times x squared plus 3, that's raised to the 5th power, plus 7. All of that is raised to the 1/2 power because of the square root. Alright, so what do I have? I have a chain rule that has a product rule that has a chain rule inside of it. There we go. That's what I was trying to say. So let's try this out. That's going to be y prime. Alright, so y prime is going to be, first off, the derivative of the outer function. So that's going to be 1/2 times x squared plus 3 raised to the 5th plus 7 raised to the negative 1/2. That was the derivative of the outer function. But now, I'm going to give myself a bracket. We have to do the derivative of the inner function. And so the inner function is all of this stuff. X times x squared plus 3 raised to the 5th power, all plus 7. So remember that the derivative of the sums is the sum of the derivatives, and the derivative of 7 is 0. So that part we get to kind of ignore, but that is at the end anyway. So now I've got to deal with what's x times x squared plus 3 raised to the 5th. What's that derivative? That's a product rule. So, product rule. That is, write our second function unchanged. That's going to be x squared plus 3 raised to the 5th times the derivative of x, but the derivative of x is 1. Ooh, that one's done. Alright, plus. Now if we were being real careful, we'd need another set of parentheses here to make up for... If we were doing another set of parentheses here, we want to be careful. We could put parentheses here and here, because realize we're really taking the derivative of that entire thing. And so I'm about to have to take the derivative of the second half, but then the derivative of 7 is 0. And so that's going to finish off this derivative. Alright, so back to it. Now I'm trying to do the chain rule. Alright, but before I do the chain rule, the first function is unchanged. Then the derivative of the outer function, well, that's going to be 5 times the inner function unchanged, which is x squared plus 3 raised to the 4th power. Then I've got to take the derivative of the inner function, but the derivative of the inner function is just 2x. The derivative of 3 is 0. And so that is my chain rule inside of my product rule inside of my chain rule. Alright, let's clean it up. That's going to be 1/2. I'm just going to go ahead and change some things. Negative 1/2, that's the square root of x times x squared plus 3 raised to the 5th plus 7. And then on top, we're left with 1 times x squared plus 3 raised to the 5th power plus 2 times 5 is 10. X times x is x squared. X squared plus 3 quantity to the 4th. I think that's about as much as I can clean it up. But there we are. That's our derivative of y prime. Alright, so now we want to find the equation of the tangent line to the curve y equals x plus 3 times x squared minus 3 to the 10th at the point negative 3, 0. They were so nice they gave us the x and the y value. So, first things first, let's find y prime. Alright, so y prime is going to be, that's a product rule, so that's x squared minus 3 raised to the 10th times the derivative of the first function. That's just going to be 1, right? The derivative of x is 1, the derivative of 3 is 0, 1 plus 0 is 1, plus, now the first function unchanged, that's x plus 3, then we have to take the derivative of this piece, but that's a chain rule, so that's then 10 times x squared minus 3, inner function unchanged, 10 minus 1 is 9, times the derivative of the inner function, which is 2x to the first, the derivative of 3 is 0. There's that. Wonderful. So we found y prime. And for all intent and purpose, since we are just trying to find the equation of the line, why evaluate the rest of this? What I really now need to do is I need to evaluate this function f prime at the point negative 3, and then whatever we get is our slope, right? And so for this, that's going to be negative 3 quantity squared minus 3 raised to the 10th power times 1, I'm not going to rewrite that, plus negative 3 plus 3 times 10 times negative 3 quantity squared minus 3 raised to the 9th times 2 times negative 3. Now I think this is going to come out pretty nicely pretty quickly, and I'll show you how. So first off, I've got negative 3 quantity squared. Well, that's positive 9. Alright, so this is positive 9 minus 3 raised to the 10th power. Now at this point, this is what I want to look at. I've got minus 3 plus 3. So this is plus 0 times a bunch of stuff. Whatever that stuff is, it doesn't matter because it's times 0. And so if we call that our stuff, 0 times anything is 0, and so that part goes away. Then I've got 9 minus 3, which is really 6 raised to the 10th power. And I get that 6 raised to the 10th power is 60466,176. And so therefore that's my slope. And so then if I want to find the equation of the tangent line to the curve, that's just going to be y minus y1 is equal to m times x minus x1. And so then this is y minus 0 is equal to 60466,176 times x minus 3. And so let's clean it up a little bit. Y is then equal to 60466,176 times x plus that number times 3, which is 181398528. And so I claim that is the equation of our tangent line to the point negative 3, 0.